Section 4.7, Medians, Altitudes, and Perpendicular Bisectors. First vocabulary word is a median. A median is a segment from a vertex to the midpoint of the opposite side. From a vertex to the opposite side, cutting it in half. From the vertex to the opposite side, going through the midpoint. The next vocabulary word is an altitude. An altitude is the perpendicular segment from a vertex to the line that contains the opposite side. In an acute triangle, the three altitudes are all inside the triangle. Notice that they go from a vertex to the opposite side, and they are perpendicular. In a right triangle, two of the altitudes are part of the triangle, they're the legs, and the third altitude is inside the triangle. The red lines show the altitudes, and the third altitude is inside the triangle. In an obtuse triangle, two of the altitudes are outside the triangle, and the third altitude is inside the triangle. Please pause the video, copy this obtuse triangle, and draw the altitudes from each vertex. A perpendicular bisector is a line, a ray, or a segment that is perpendicular to the segment at its midpoint. In a given plane, there is exactly one line that is perpendicular to a segment at its midpoint. In this picture, DC is a perpendicular bisector of AB if and only if it goes through the midpoint and creates right angles. In a triangle, the perpendicular bisector does not always go through a vertex. First theorem, perpendicular bisector theorem. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. Watch what that means. Point A lies on line L, the perpendicular bisector. We know it's the perpendicular bisector because it created two congruent segments, and it was going through line segment BC, creating right angles. That means that point A is equidistant from both point B and point C, the endpoints of that segment. So AB is congruent to AC. Point A lies on the bisector. It's equidistant from B and C, the endpoints of the segment. What theorem can you use that would prove that that was true? Think about your triangles. Likewise, I can pick another point that lies on that perpendicular bisector. If I pick a point D that lies on line L, it's lying on the perpendicular bisector. That means that point D is equidistant from both point B and point C. Line segment BD and line segment CD would be congruent. The perpendicular bisector theorem converse says, if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of the segment. Given a point A, it's equidistant from point B and from point C, meaning AB and AC are congruent to each other, forming an isosceles triangle. Then point A is on the perpendicular bisector of line segment BC. Before we can move on, we need to talk about distance. Distance is always the shortest distance between 2 points. That's how it's measured. And in any kind of geometric shape, distance refers to the line segment that is perpendicular from a point to another line. Same thing from a segment to a segment, the shortest distance is always going to be perpendicular. Angle bisector theorem says, if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. Given line segment BZ is the bisector of angle ABC. Point P lies on the angle bisector. Therefore, point P is equidistant from the ray BA and ray BC. It's equidistant from the two sides of the angles. Therefore, PX and PY are congruent. The converse says if a point is equidistant from the sides of an angle, then the point lies on the bisector of the angle. What you're given is that PX is congruent to PY. It's equidistant from the sides of the angle. Therefore, point P lies on the bisector of angle ABC.